All right. Hello, everybody. My name is Marcia Chechuk, and it is my great pleasure to present to you Professor Jeannette Wing. Jeannette Mary Wing is the Executive Vice President for Research, Abanation Director of the Data Science Institute at Columbia University, and she's also a Professor of Computer Science there. Until June 30th, 2017, she was also Corporate Vice President of Microsoft Research, with oversight of its core research laboratories around the world and the Microsoft Research Connections. Prior to 2013, she was the President's Professor of Computer Science at Carnegie Mellon University, and she still has the adjunct appointment in CMU. And during this time, she also had a couple stints as chair of the Department of Computer Science. She also served as Assistant Director for Computer and Information Science and Engineering at NSF from 2007 to 2010. Jeannette has had a long and illustrious career in the area of formal methods, starting probably with her thesis work on the large theorem prover, the broad work on popularization of Liskov's substitution principle, and her incredibly influential work on generally popularizing formal methods and making them scalable and integratable with other software engineering principles. For example, as you remember from yesterday's banquet, she co-organized with Jim Woodcock the first World's Congress on Formal Methods, FM23, and incidentally, this was the very first time that I attended FM. She also co-authored a couple papers back in 1996 that I think have become a required reading for FM students around the world, including my own. One with Jonathan Bowen, Ricky Butler, David Dill, Robert Glass, David Grease, Anthony Hall, and others, called Invitation to Formal Methods, and another one with Ed Clark, Formal Methods State of the Art and Future Directions, as part of ACM Computing Surveys. Jeannette Wing has been recognized with Distinguished Service Awards from CRA and ACM. She is fellow of AAAS, ACM, and IEEE. Her essays, From Computational Thinking to 10 Research Challenge Areas in Data Science, affect education, funding, policy in institutions around the globe. The title of today's talk, which FM organizers called Luminary, is Trustworthy AI. And incidentally, this also fits with the theme of this year's FM. Welcome.
Thank you very much. And I am looking at the little FM23 speaker view, and it looks like there's a nice audience. So first of all, I'm very happy to have been invited to FM23. I really wish I could be in Lubeck. I once visited and I was looking forward to visiting again, and I understand you have some wintry weather, so that would have been fun because we're not getting a lot of snow here in New York. So let me start. I am going to talk about trustworthy AI. And I want to start, however, with my history with formal methods, this conference. And it actually starts before 1999. Okay, let's make sure I can advance my slides. It starts with FM89. Now, if I were there, I would ask in the audience, how many people even heard of FM89? Well, I'm asking the question, I don't know if I can see your hands, but FM89 to me was the inaugural formal methods symposium or conference. And it was held in Halifax, Nova Scotia, and it was an invitation only for people from the US, the UK, and Canada. And it was in that conference that, and then was FM99, which was mentioned already. Jim Woodcock and I were co-program chairs. And what I remember of FM99 was flying to do the paper selection, flying into London, taking a train, being really, really tired. But Jim and I, and also Dinas Bjorner were there. Dinas was general chair. And by the way, he says hello. And I remember, having a wonderful, couple days doing the program, the paper selection. And I remember one thing that Dina said to Jim and me, and this is 1999. He said, "Oh, formal methods, it's just a given. Everyone uses it now. It's sort of in practice." And Jim and I just looked at each other thinking, no, we still have a long way to go. And sure, given that we have an FM23, I think we do have a long way to go. And then finally, in 2009, I was invited to give an invited talk, and this time it was in the Netherlands. And I just wanted to share with you a little snippets from these Springer Verlag volumes. In the FM89 invited only symposium that we held on formal methods, I actually was the one asked to give a talk about what is formal methods. So all of you in the audience might think this is a silly question, but back then we were still struggling with what is a formal method. And so I gave a talk about that. I actually went back to see what I said, and it's not too embarrassing. So that's a good thing. In FM99, Jim Davies and I wrote the preface, and the first sentence sort of was suggested by Dina's for us to kind of give some optimism to formal methods. And so the first sentence says, "Formal methods are coming of age." I think that's a fair compromise. And then in the talk that I gave in 2009, it was a joint paper invited by the conference organizers. And by then I had already been doing work in security and privacy, and I was just starting to figure out where could formal methods play a role in privacy. And so my student at the time, Michael Chance, and I wrote a little article trying to enumerate areas where privacy could benefit from formal methods and where formal methods could help privacy. So that's my history with the formal methods conferences, and that's why I was so delighted to be asked to talk to FM23. It's just sort of in my it follows my professional career, I suppose. And in fact, I was even more delighted that the conference organizers said that I could talk about trustworthy AI, because that's what I've been thinking about for a long time. And it is, it's something that I really encourage the formal methods community to help the AI community and help society make progress in. So let me start by motivating it, and this is not going to surprise any of you. We already know that AI achieves or exceeds human performance. AI systems can recognize objects in the street. They recognize speech in our living room, and of course they can beat the best human Go player in the world, although that's also changing. And AI has a promise, and I do believe this, of benefiting humanity and society. Self-driving cars, although that's taking longer than we would have expected, can save accident deaths. In the medical arena, we're already seeing front page articles about how AI are going to potentially replace radiologists. This is an example from a study in Cleveland Clinic on brain scans, and the AI system outperformed the neuroradiologists. In the criminal court system, the promise of AI was that it would even out the playing field where human judgment can be uneven. And then in terms of hiring, again, whenever there's human judgment, one can imagine that people vary in their application of evaluation criteria, and individuals vary over the course of the day or over their own lifetime. So AI systems or any automated system can help reduce that variation. That's the promise. We also know that we can very easily fool the image system of a self-driving car by just putting duct tape on a stop sign, and the vision system won't think it's a stop sign. We can add noise to images, and the classifier will get fooled into thinking that a benign tumor is actually malignant. We already know how much bias there can be introduced in automated systems, let alone AI systems, and where these systems are used in the criminal court system in the United States. And we also know that AI systems that are used in recruiting and hiring can be biased as well. So why should we trust these AI-based systems? So my question to you, my question to the community, and my question especially in the light of the advances of AI technology and how fast things are moving, is how then can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? And the reason I think it's such a natural domain for formal methods researchers to consider is formal methods have always found their niche in life-critical and safety-critical properties of computing systems. So it seems that we have some expertise, we have a framework for thinking about this, and we should be communicating and sharing our sensibilities and perspectives with the AI community and the rest of, and the users of AI technology. So I wanted to take a step back and give a framing on trustworthy AI in the context of trustworthy computing. This is an area that has really blossomed since around 1999, when the US government, when industry, and when academia were really pushing on the notion of trusted computing, trustworthy computing, trusted systems. There were National Academy reports out. The National Science Foundation started new programs in trustworthy computing. And the academic community already had been thinking about what does trustworthy computing mean. And just to show my bias, I really think it was Microsoft that led the computing industry. So now I'm talking about industry in terms of trustworthy computing. And if people remember, back in 2001, Bill Gates put out a memo called Trustworthy Computing. And there were 4 pillars of trustworthy computing. And it was actually quite an interesting memo, and quite interesting that Microsoft had put it out. And there was good reason that they did that. And I can share that if you ask me later. But I was at Carnegie Mellon at the time, and I thought, I wonder what Microsoft means about what trustworthy computing means. So that's actually why I went in 2002 to 2003 to spend a sabbatical at Microsoft Research to figure out what does Microsoft really mean by trustworthy computing. In any case, trustworthiness for computing systems has come to mean a set of properties that we pretty much continue to pound on, but we pretty much know that if you want to say a computing system is trustworthy, you mean the set of properties. Reliability, does it do the right thing? Safety, does it do no harm? Security, how vulnerable is it to attack? Privacy, does it protect a person's identity and data? Availability, that's the eventuality property. Is the system up when I need to access it? And usability, can a human use it easily? That's the squishier property, but it's as important for trustworthiness, especially trust by your customer and trust by the user. And computing, in the beginning, it really focused on hardware and software, but in this day and age, you have to include the people in the computing system. So from trustworthy computing, what could we possibly mean by trustworthy AI? And what I'm really doing is raising the bar. So not only do we want all those trustworthiness properties from trustworthy computing, but we're adding more. We're adding more because we're demanding these sorts of properties of the AI systems that are already in play. Accuracy is really the gold standard for any machine learning classifier at this today. It continues to be a property of interest. But the properties of trustworthiness that people are concerned about are properties like robustness and fairness, accountability, transparency, interpretability, explainability, and now, if you will, even squishier properties like ethics. So, for instance, by accuracy, I mean how well does the AI system do on new, unseen data compared to data on which it was trained and tested. Robustness, how sensitive is the outcome to a change in input? Fairness, are the outcomes unbiased? Accountability, who or what is responsible for the outcomes? Transparency, is it clear to an external observer how the system's outcome was produced? Interpretability or explainability has to do with, can the system's outcome be justified with an explanation that a human can understand and or that is meaningful to the end user? And then there are ethical issues like, was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And so on. So the question of how can we achieve trustworthy AI, especially for this audience, my home audience, I think of formal methods. Of course, I'm going to say, well, one approach is through formal methods. And that leads one into a series of questions and framing and questions of, well, what would it mean to apply the sensibilities of a formal methods framework, for instance, to trying to make an AI system trustworthy? So the next series of slides are not going to surprise this audience, but it's a way of my walking through that thought process. It's going to be mainly open research questions. So I hope there's some students in the audience who are looking for a PhD theses, because I don't know the answer to any of these questions. So let me start with the canonical framing of formal verification or formal methods. And I characterize it in terms of what's in that red rectangle, M satisfies P. We all know what this means, but this already is something that might not be understood by the community outside of formal methods. So M, of course, it could be a program, a piece of code. It could be a protocol written in some kind of abstract model of a system. It certainly is, say, like a state machine. Or a Petrinet, whatever your model is, some abstract model of the system. And often today it would be a model of a concurrent or distributed system. But M is essentially a mathematical object, or an object that can be described mathematically. P is a property of interest. P is often, and in the traditional sense of formal methods, described in some kind of discrete logic, usually a Boolean logic, could be a temporal logic, but it's a true or false. You get a true or false, or maybe you get no answer. But in any case, you get some Boolean as an answer if you get an answer. And P, we have studied P since for decades. Obviously, temporal logics have been a very good source of expressing properties, P. So we can, and then many theses have been written and papers have been written on the characterization of these kinds of properties we care about for systems correctness properties, like dividing it into safety properties and liveness properties. And just decades and decades of work have gone into different kinds of M's and different kinds of P's. And of course, what's tying it all together is some logical framework, which I use the double turnstile to denote. So that's the satisfies, M satisfies P. And again, decades of research have gone into many logics and tools that embody these logics and allow one to verify automatically or semi-automatically or with a lot of manual effort whether some model M satisfies some property P. And so much progress has been made, especially since 1989, let alone 1999, on M, P, and satisfy. So this is just, you know, a given. We know how to do this. And it is a matter of scaling it up in education and so on. And we still have those challenges. And of course, the systems that we're modeling get more complicated and so on. But we know how to do this. Now, what about for AI? Oh, yes, one last thing is sometimes we explicitly model the environment of the system that we care about. And so we will have an additional formal object, E, to stand for the system environment. And very often for parallelization, we might say E, you know, in parallel with M satisfies P. So what about AI systems? Oh, and this is the canonical, I'm going to just belabor this M satisfies P in terms of model checking. You're all familiar with this very old technique where you have a model like a finite state machine. I'm just making it concrete. A P is expressed in some temporal logic. You push the button on the black box and out comes yes. Every behavior represented by the state machine model M satisfies the desired property P, or no, and not just no, but you get a counterexample, a sequence of states that at the end state P is falsified. So this is just, you know, I know you all know this, but I just wanted to make it concrete. So, okay, what about AI systems? And again, I'm kind of raising the bar on what does it mean to verify an AI system where the kinds of properties that we care about are not just the properties we had for trustworthy computing, but these additional properties like robustness and fairness and so on. And we need to reinterpret what M and satisfies are. So M, for the purposes of this talk, I'm thinking about a machine learned model. Obviously, AI systems are much more than machine learning, and it's not just DNNs. But to make it concrete, think of a DNN in your head that's used for classification or prediction. Now, what gives me hope, although I will talk about some challenges, what gives me hope that formal methods are even applicable, and then I can talk about M as a mathematical object, is that in the end, these machine learned models are a piece of code. So it's a program. It's not a program that a human being wrote. It's a program that a machine wrote. But still, it's a program. It's a piece of code. It's a mathematical object. I think what is interesting for AI systems is the inherent probabilistic nature of these systems and the probabilistic nature, in fact, of the properties we care about. And these properties can be expressed in terms of probabilities or more likely data distributions or stochastic processes. And so these are kinds of objects that we didn't have to deal with in the past in traditional formal methods. And I also think that the kinds of logics and logical frameworks we might use for double turn style need to be rethought. We can definitely appeal to probabilistic logics and probabilistic logical frameworks and tools for probabilistic logics, but we might need new kinds of reasoning. And these are the sorts of questions I'm going to get into for the remainder of my talk. Now, I think the most important difference between traditional formal methods, where we're kind of in the Boolean world and we're in a very nicely defined world of mathematics for representing the systems that we care about, the M's, is the presence of data. So D in some sense is my analogy to E in the old world. D is used to test and train the model, and more importantly, it's the data that we haven't seen yet, for which the M satisfies P must hold. So that seems to be very different and a challenge, and perhaps the most significant challenge to the formal methods community. So we need a model of data and one you can think intuitively could be a stochastic process or distribution. And it's the data that this model should be generating, the data inputs on which M's outputs need to be verified. So this, in a nutshell, is what I mean by applying or using a formal method sensibility towards trustworthy AI. So just sort of let that sit with you. DM satisfies P. And what I'm going to do is walk through the questions for what this all might mean in terms of formal methods. So let's start with two main differences, which I've already alluded to: the need for probabilistic reasoning and the role of data. So the need for probabilistic reasoning, first, let's look at M. M is semantically and structurally different from a typical computer program. Yes, in the end, M intuitively is just a program. But first of all, M is inherently probabilistic. For instance, for a DNN, you've got the edges between the nodes are, probabilities are running all over that neural network, and you're outputting probabilities. Structurally, M is machine generated, and it's unlikely to be human readable. Now, for our community, I think of it as another kind of intermediate code. And our community is very good, and especially the programming language part of our community, static analysis, dynamic analysis techniques can potentially be used or reinvented for running around this kind of intermediate code. That's kind of stuff that we're good at, so we should be thinking about that. And then, of course, M is, we are putting this AI system in the context of an uncertain environment. So we need to reason about the uncertainty of M's environment. And the only way computer scientists know how to reason about uncertainty is to model uncertainty as probabilities. P, what about P? Well, P, interestingly, may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So I'm actually saying more than the need for probabilistic reasoning here. I am saying the need for reasoning over continuous domains. For instance, robustness properties for DNNs are characterized as predicates over continuous variables. So it's no longer going to be easy to just talk about discrete domains. Fairness properties, the most well-known fairness property, differential privacy, is characterized in terms of expectations with respect to a loss function over reals. So again, if you really want to model something faithfully in terms of what the math says, we can't avoid this continuous domain. That was the differential privacy point. The fairness properties are characterized in terms of expectations with respect to a loss function over reals. And these are many of you are probably familiar with the YouTube video on 21 notions of fairness. These 21 notions of fairness are all mathematical definitions of fairness, and each definition and each notion of fairness is perfectly rational. Unfortunately, they all some of them are inconsistent with each other, but in any case, they're very similarly characterized. And then the notion of privacy that I mentioned already, differential privacy, is defined in terms of a difference in probabilities with respect to a small real value. So what I'm getting at is these properties P that all of a sudden we need to care about for trustworthy AI, robustness, fairness, privacy, and so on. We can't avoid having to talk about these properties in terms of continuous variables or continuous domains. And then finally, for satisfies a double turnstile, we can, the good news is the formal methods community has not been, has been working on probabilistic and hybrid logics for decades. So we have a lot to build from. We're not starting from scratch, but we can now start, using these sorts of framings to build on how we might think about formal methods for trustworthy AI. So we have probabilistic logics and hybrid logics, and we just need to scale them up, or maybe we need to invent new verification techniques that work over reals and nonlinear functions like sigmoids and so on, work over probability distributions, and that might be something new and different. And so just to make my point in terms of, we've been working on these kinds of logics for decades. I go back to Tom Hensinger's PhD thesis, 1996, where he introduces the notion of hybrid automata, where this is taken from his thesis, where you can express the continuity in your system, the continuous behavior in terms of differential equations in the states, and then you have these jump conditions that are the kind of discrete transitions between states, something very familiar to all of us. And you can even have invariants that might hold across all states within a state. And then there's a lot of tooling that's happened since hybrid automata has been introduced, and these are just some of the names of the tools. If you want to stick to more a logical approach rather than a model-based approach, then my colleague at Carnegie Mellon, well, he has an appointment also, I think, somewhere in Germany now. Andre Platzer is famous for differential dynamic logic, and the beauty of this approach is that in one logical framework, you can talk about both the continuous and the discrete behavior, and on one logical framework, you can write the model that you care about and the property or the formula P that you care about, and do the reasoning in one single logical framework. And this too has been applied to many life-critical, safety-critical systems, and there's tooling, and there's a fat book that Andre so nicely sent me after he finished authoring it.
By the way, Jeannette, he's in the audience.
Oh, Andre! I hope I didn't say anything wrong.
Sorry.
Okay, so Andre can answer all of the questions that on differential dynamic logic. So, and then there's reasoning about uncertainty, which I mentioned already. And, the programming language community especially has not been lazy about this. They've invented probabilistic automata and probabilistic model checking, probabilistic logics, and probabilistic programming languages. This is a little snippet of a probabilistic programming language that was invented during my time at Microsoft Research. And there's these variables, Boolean variables, that can range over distributions. And you flip a coin and you get some assignment to C1 and C2, and then you observe one or the other. And it's deliberately written like in a C-like style, so that it just slips into a C-like programming model. There are many probabilistic programming languages that have been invented and used for different applications, but I would say there are no. It's not commonly used, and there's one probabilistic programming language, or maybe two, I should say. There are two probabilistic programming languages that have kind of gone beyond a paper. And some papers. One is infer.net, which came out of Microsoft Research Cambridge, which was used for very interesting applications. And probably the most common probabilistic programming language actually came out of the statistics community. It's called STAN. And my current PhD student is actually adding programming language features to STAN. This is a marriage of programming languages and statistics. But in any case, we haven't been sitting still in terms of reasoning about uncertainty. Now, what about the role of data D? This to me starts is a conundrum, and it starts. I start scratching my head. I just did that when I think about how to characterize D. So let me first say I want to distinguish between available data and unseen data. Available data is data at hand, used for training and testing. That's like data we see. Unseen data is data over which the machine learned model M needs or is expected to operate without having seen it before. That's the whole idea of using a machine learned model, so that you can use it for system in the world or on data that you haven't seen before. You can classify it on images you haven't seen before. So the collecting and partitioning data, there's some obvious questions. How do we partition an available data set into a training set and a test set? And in terms of formal methods, what we might ask are, what guarantees can we make of this partition with respect to a desired property P in building a model M? Or how much data suffices to build a model M for a given property P? This is something, of course, the AI community asks of itself all the time. Is there an opportunity for the formal methods community to say something more definitive? Does adding more data to train or test a model M make it more robust or fair? Or does it not have an effect at all with respect to the property P? And what new kinds of data needs to be collected if a desired property doesn't hold? I'm going to get back to that later. Now here is, I think, really hard. This is the heart of the problem that I scratch my head over a lot, which is specifying unseen data. This is the real issue. How do we specify D, where D stands for the unseen data? So how do we specify the data and or characterize properties of the data? Now, one approach is specified as a stochastic process or a data distribution, for instance, via its parameters. So a normal distribution, standard deviation, and mean, or something like that, easy. Probabilistic programming languages, I mentioned STAN already. It's already being used to specify statistical models. Is there a way to combine these probabilistic programs with our M satisfies P framing and conjoin them in some meaningful way? I don't know how to do that. But I think the real challenge is the large real-world data sets that don't fit into common statistical models, or which have thousands or now millions or trillions of parameters. So that, to me, we just don't know how to do this. Do we need new math? Maybe we need new math. We just don't know how to do this. So that's why everything is experimental and observational, but there's nothing formal. And that's a little unsatisfying. And then here's the real, the problem I get into, which I don't know how to get out of, and I need your help. So there's a little circular reasoning that we need to break. To specify unseen data, we need to make certain assumptions about the unseen data. But then would these assumptions not then be the very same as those we would need to build the model M in the first place? So on the one hand, this is the canonical formal methods problem where you need to trust the specification of D, much like we trust the specification of M and P and E in our traditional sense. So maybe we can just punt and say, but we've always had this problem. You make some assumptions and you have to trust that those assumptions hold, and you use something else to discharge those assumptions. So that might be one way to break the circular region. But I think there's something subtler and different in, the situation of the kind of D we're talking about. Anyway, all I can think of are, these techniques. One is in the spirit of using a completely different approach for discharging the assumptions. We can use a repertoire of statistical tools that the statistics community has been using for decades. Maybe that can help. Another is something more common to all of us, which is analogous to the counterexample guided abstraction and refinement method in formal methods. You assume an initial specification, and this initial specification is small and simple enough that we can check it manually. And then we use that specification to bootstrap in an iterative refinement process, the specification that we really want for D. I don't really know. And then finally, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? So if we do use something outside of our realm, we need to connect the logic, the math, and make sure it all makes sense. So here's another interesting difference or question. What do we quantify over? In traditional formal methods, we strive to prove for all x p of x. It could be for all values of a variable x, p holds of x, and we overprove because we know not in a piece of code, not all values will be touched. But if we prove for all x, then we'll be safe for any value over which that piece of code runs. For a concurrent and distributed system, we mean for all behaviors, x, p of x holds. So we've always been safe. We've overproven what we need to prove, and then we're done. And that's very comforting. But for AI systems, it's a little different, and this is a bit of a hedge, and I don't really know if I'm hedging or if this is just the way it is. We do not expect M, this machine learned model, to work for all input data for all data sets D. Now, maybe we can use that to our advantage. So let me just be a little more pedantic. This is the canonical for all x p of x. And let me break the quantification in the p of x out and say something like, maybe this specification of D is about what are we quantifying over, and then P of X, we already know that's the specification of the property, and we have formulas out there for fairness and robustness, and we know how to handle that. So what we really are trying to figure out is how to combine some way of a quantification for that property. So on the one hand, we've got X. On the other hand, we've got for all x. And let me, in terms of probability distribution, say the analogy would be I sample from a data distribution D some x. Or I might say, for all data distributions, I sample. And for robustness, the latter makes very good sense. I might say any arbitrary norm-bounded perturbation. So, for example, changing pixels to an image should not change the classifier to say it's not a stop sign if it's a stop sign, or it's not benign when it is benign. And then for fairness, this is the kind of property that people have been writing papers about in the AI community. Given a fairness property like statistical parity, given a data distribution, you would say this machine learned model is fair. But it's fair with respect to a given notion of fairness, that's okay. But with respect to a set of data. So you tried over the compass data, you tried over some other data, and you say it's fair. And you kind of just walk down the D's that way. So obviously, I leave a gap in the middle because that's where I think we should be focusing on, and that is something in the middle where it's for all data distributions over a class of distributions, we can prove something about, we can prove P of X. And so, for instance, for robustness, we don't want any arbitrary, maybe not any arbitrary norm-bounded perturbation, because for the context or the task at hand, we don't really, it doesn't have to be robust with respect to those perturbations, but rather what we care about is robustness with respect to semantic perturbations. So if you think about a car and you're looking at a self-driving car, looking at a car in front of you, if the car in front of you has a dent in the fender, you still want to classify it as a car. And that's a semantic perturbation because a dent in the fender is meaningful for an image of a car, and it's semantic also with respect to the context because you're driving along on the road. Obviously, you would say it's you'd have a different classifier to say if you take this car with a dent in the fender to the repair shop, you want the repair shop to say there's a problem with this car. So that's what I mean by semantic perturbation in a case. You don't change any old pixel. You change pixels that are relevant to the task at hand or the object class at hand. And then in the other direction is fairness. What you really want is a classifier that we can deem as fair, that is fair for distributions over which we tested and trained and nearby distributions. So that is kind of what I mean by for all distributions in a class of distributions. And then what we just need to define is what we mean by that class. So just to be a little more concrete, I want to give two examples of why this idea of what do we quantify over might be property dependent. And I already hinted at this. So for robustness in the adversarial machine learning model, we might want to show that M is robust to all norm-bounded perturbations D, but more interestingly, we might want to show that M is robust to all semantic or structural perturbations to the task at hand. And the example I gave with the car is really an example for computer vision. The example for fairness actually is something that colleagues of mine at Columbia and I worked on, and this appeared in NeurIPS 2020 or 2021 or 2020, can't remember. And what we did was we looked at these scenarios where machine learning classifiers were known to be unfair. And what we did was we built classifiers that were not just fair, but robustly fair, so that we could show for a given ML classifier that it was fair with respect to nearby distributions. And the way we did this was a pretty canonical approach in machine learning, which is to use an online algorithm or two-player game approach to build a fair classifier that is robust to a class of distributions. So it was exactly what I was getting at before. Okay, so now let me talk a little bit about the verification task, the double turnstile. How do we check the available data for desired properties? For example, if we want to detect whether a data set is fair or not, what should we be checking about the data set? If we detect that the property doesn't hold, how do we fix the model? This is equivalent to, you press the button on the black box, the model checker, and a counterexample comes out. You use that counterexample to help you either fix the model or amend the property. So how can we What is the equivalent of a counterexample in case a verification doesn't hold, and how do we use it? How do we exploit the explicit specification of unseen data to aid in the verification task? How can we extend standard verification techniques to operate over data distributions, perhaps taking advantage of the ways in which we formally specify unseen data? I wanted to also, call out a colleague of mine who's been working on a verification technique called interval analysis, which works over intervals of reals. And he's been using this technique to show robustness of deep neural networks. And it's a highly parallelizable algorithm, and it works. And this is old results already, but at the time when it was published, it worked over 200 times faster than state-of-the-art SMT solver-based approaches. And I'm not going to go through the example, but it's quite a easy to understand algorithm, easy to implement algorithm. And the question here is scaling it up. And I think the other interesting question, which I challenged my colleagues to think about, is right now these intervals are over reals. What would it mean to have intervals over probability distributions? So instead of a, E lower and E upper, you see some sort of class of distributions lower and class of distributions upper, or something left and right. I don't really, up and down, I don't really know, but what would that mean? And then what would it mean to propagate information across these symbolic intervals? Popping up a bit, I think there are more opportunities for formal methods beyond the kind of the post-facto verification approach that I've talked mostly about. There's task specific. I alluded to that already. I think that's where we're gonna make progress, much like we did in the old days in formal methods, where we would fix on a sector like safety critical. There's also model synthesis, which is, I think, something that the AI community would very much embrace. And that is the correct by construction approach, where you start with your specification and you have a desired property, and you generate your machine learned model with that desired property in mind every step of the way. So you don't have to prove anything at the end. You know it's correct at the end by construction. This is the program synthesis approach. There's the compositionality, holy grail of formal methods, where you don't want to redo the reasoning. You want modular reasoning. You want local properties to imply global properties, et cetera, et cetera. So all of that still holds. Lots and lots of room for lots of opportunities for formal method sensibilities to help the AI community with their massive monolithic machine learned models. And then this statistical approaches I mentioned earlier, just list some of these here: sensitivity analysis, prediction scoring, predictive analysis, residual analysis, and they have a technique called model criticism. All of these are well known in the statistics community, and something I think the computer science community, the AI community, the formal methods community, trustworthy computing community can all benefit from. And a correct by construction example, I wanted to give you an example of robustness by construction, and this is work done by my colleagues here at Columbia, and this is inspired by differential privacy, but it's actually a way to make a DNN robust to input perturbations. And the idea is to add a layer of noise, a la differential privacy, in the DNN. In this particular case, she and her colleagues determined that adding the noise layer right after the first layer of the DNN is the most effective. And because you can control exactly what noise you're adding, you can then control, it's like a knob of how robust you want your outputs to be with respect to perturbations to the input. I think this is really nice. And the point is, by the time you finish constructing this DNN, you know it's robust with respect to certain input perturbations. So that ends my talk. I just want to end here. This is the whole point of my talk, Trustworthy AI meets formal methods. So thank you very much.
All right, thank you so much. Questions? Andre.
Thanks, Jeannette. This is Andre. Thanks for a wonderful talk. I have a question about one of your slides, differential lemming logic. No, I'm kidding, of course. I have a question about something you mentioned as the holy grail, formal methods, the compositionality, where I would add to that to some extent. I think induction is maybe the most beautiful part of that, where we do reason about the big thing by just reasoning about the small thing. For data-defined systems and AI systems, that notion seems very difficult. For instance, as you've just explained to us, robustness notions themselves are inherently not like that at all, because robustness is not robust itself. So it can never quite survive an argument where you reason in about something large by reasoning in the small repeatedly often. Do you see any light at the end of the tunnel, so to say, getting these properties worked out in AI as well?
I think, thank you for the question, Andre, and I wish I could see you. It's so nice to see you, Andre. There's a very common, I'm now speaking beyond my expertise, but there's a common machine learned approach called federated machine learning, which almost suggests some kind of compositionality if one can figure out what exactly that compositionality property is. And maybe that's one place to start because it's so obviously distributed. And is there something that one can prove about the individual components that would let you infer something about the federation? I don't know. That seems to be why people are using federation, and maybe it's a privacy property, but that's the first thing that comes to mind. But I do think when I think about a large language model that has, to come, GPT-4 is likely to have 1 trillion parameters. I think we have the vocabulary to talk about modularity and compositionality, induction, and so on. Can we do more than suggest vocabulary, but actually suggest methods and algorithms and tools so that we can help the AI community reason about their systems in some meaningful way? I think I really think it's up to our community and our being formal methods, programming languages, software engineering, to come to the table and try to understand how can we help? Because the world needs our help. That's how I feel.
That's a cheerful thought. Thanks, Jeannette.
All right, other comments? Wolfgang.
Thank you for a very nice talk. So one could generalize the question. You talked about trustworthy AI, and we can talk about trustworthy trust in systems which use AI. And one answer to that, one approach to that is everything you talked about. And that's the hard part, but super interesting part, right? Where by having trust into the AI components. And That's fantastic. But I think there's this other thing which I think we should still be doing and focusing on and do more of. And that is, there can be systems. How can we have systems which use AI and we trust the system, not by trusting the AI, but how can we safeguard the AI? And yeah.
Yeah, that's a very good point. And I thank you for asking that, because I forgot to make that point. And there has been progress in that approach. And I don't know if Sanjeev Sesha is in the audience, but he to me is my hero in kind of looking at trustworthy AI systems, where he's looking at systems that use AI. And is Sanjeev in the audience? I don't want to speak for him.
No.
Okay, fine. Then I'll speak for him. And he's at Berkeley. I think you all probably know that. And he's been looking at autonomous systems, cyber physical systems, and he's been treating the AI part of those systems as black boxes. So you just observe the behavior that surround that black box, and then that's just part of the bigger system. And then you can use more traditional formal methods techniques to prove properties like robustness properties of those systems. And that's actually what he's done. He's used simulation to synthesize behaviors of such systems that have AI modules as black boxes, and then can verify robustness properties. So that's a very, very, very good idea. That is also a place where we can make progress and show that our techniques can do something useful to the AI community. And maybe then that will be an invitation to, well, can you actually say something about that black box?
Right. Okay. Thank you. Right.
All right, Carla?
Yeah, thanks again for a very nice talk. So you presented a very broad overview of many very challenging problems that we have to face. And of course, we're not going to solve all of them at once. So I was wondering if you think there are some that are in a way more urgent or more critical to kind of like make progress towards this view of trustworthy AI, or maybe you cannot really prioritize and we're going to need more or less all of them.
I have this high level, wish, which would, I think, mean everyone in the audience has a part to play. And I just, there's no reason today that we should trust AI systems for anything. And on the other hand, there's so much that we can do with AI, and it's not going to go away. It's their uses, and it's already pervaded everything we do. And they're going to be in more and more of the systems that are going to make decisions about people, about our lives, and the industry and government are embracing these systems, not necessarily because they should, but they are, and we are as customers and users. So I just want all of us in the formal methods community to help the world have some assurance that they can trust these systems for something. Now that's the bigger goal. And the reason I say every one of you in the audience has a particular expertise and a particular interest, maybe just think about how that is applicable to AI. That's not a really good answer. I get stuck on the questions that I scratch my head over, but that's just because I led myself to that. I think every other person in the audience probably is thinking about their own area and expertise. And if you think about, well, how would this be applicable to an AI system? Maybe then we can make collective progress in parallel, because AI systems are surpassing, they're advancing so quickly. And I do want, we need to embrace this revolution. So I know that wasn't a good answer. Sorry, I never got that question before, so I'll have to.
We just have to get that work.
Yeah, I wrote that Trustworthy AI paper because I was very, very anxious. That was a few years ago, and I'm even more anxious. And who would have predicted GPT-3 or GPT, 4 months ago? That's how, and GPT-4 is coming out soon. And it's going to be it's already in our search engines, and it's going to be in Word and PowerPoint and Excel.
All right, other comments? Okay, I wanted to maybe ask also a question, given that I have the mic. I guess I have two questions maybe. One of them is a commentary on compositionality. It's more a comment than a question, that compositionality within the AI space seemed to be observable in a couple places. One is, we are composing layers. So you could imagine, composing analyses sort of ish, and some people are doing this. And in the world, for example, of not quite robustness, but reliability, as in being able to have predictable analysis subject to the world's perturbations, those are composable. So, if you can imagine that it is raining and dark, well, you can analyze what happens under rain, you can analyze what happens under dark, and then you can start composing these things. And that's very much the formal methods kind of way of thinking. But my comment is the following. Formal methods, and I think this is related to what Carlo is trying to say. So the formal methods made progress by focusing very precisely on safety critical systems, and started making even more progress where regulators or assurance or whatnot directly mapped costs of failure to costs of development, and therefore made an economic argument that it is worth investing in specifications. If we start with partisan nuclear power plants and stuff like that, basically focusing where the trade-off is absolutely obviously into the favor of trustworthy software engineering. With the prevalence of AI, what domain do we start with where we may have such a hope? I mean, a lot of us are working on autonomous driving, but there is so much happening there and so fast that I don't know if we are being taken very seriously.
I would look into where AI systems are being used potentially in healthcare applications. I think everyone probably saw the articles recently about, will AI systems replace radiologists? Now, I think all of us would agree that they're not going to replace humans, but they will be used to enhance the diagnoses. Humans and AI systems will be used together. But that's a sector that's also highly regulated, and people's lives are going to depend on these diagnoses. And this is, again, where interpretability and explainability would be super helpful, at least for the doctor, but for certainly the patient. So that's an area, perhaps, a good area for the formal methods to think about. I do agree with you that progress in formal methods has been made because of the cost-benefit trade-off for safety-critical, life-critical systems. And by the way, that's still there. I did want to take this opportunity to say that I think the property that's the hardest is fairness. Not just that there's so many formal notions of fairness, but even if we were to build a fairness verifier, that system still has to be used in the context of making judgments about people, possibly in the context of ambiguous laws. And, you know, this is where the connection between computer science and law and policy will be very important for, you know, why would a jury trust a, you know, the technical expert that says, well, this machine learning classifier was deemed fair by this, you know, verification system. But what's a jury to make of that? And how are the two sides of the case going to defend or attack that statement? So the reason I say this is that when I talk to my colleagues in the law school at Columbia, they kind of tell me this: oh, you can do all you want, you know, to deem some machine learning system is fair, but that may not hold in the court of law. That surprised me because, you know, as computer scientists, we like things that are black and white. But in law, they like to have multiple interpretations of something, so that on purpose, they do that on purpose. And I'll tell you another thing that I think is very difficult. And that is, this is all this fake news and how to determine whether something's real or not. And AI systems are going to be generating more and more silly stuff that's not real. I don't know if, I haven't thought hard about where formal methods fits in there, but I know it's a hard problem.
Thank you. Thank you so much for this honest answer. I think we were thinking through this with you, and this was, you know, amazing. Any other comments? Okay, so I think this is fair to thank you on behalf of everybody for delivering what has been specified, which is luminary and thought-provoking talk that gets us all thinking where we fit, where do we go from here, and, you know, how next FM will be the FM of, you know, many successes in trustworthy AI.
Yeah, that would be great.
Thank you again for joining us. Thank you for speaking to us. And we really wish you were here in person to continue this conversation.
Me too.
But we make the best out of the circumstances. Thank you again.
Thank you very much. Bye-bye, everyone.